Hello world, and welcome to my presentation. It is an amazing pleasure to be part of this very first edition of PyData Global, and it is even better to have you guys here today as part of my audience, so thank you. So for today, I have a very nice and even fun presentation, which I'm calling Is a Neural Network Better than Ash at Detecting Team Rocket? And if so, how? Now, my name is Juan, and I work as a data engineer for LOVOO, which is a dating and social application based in Germany. However, for today, I would like to remove this title and call myself a Pokemon data professor because I'll be talking about Pokemon and data. So if you're ready, follow me. And I want to start with a bit of backstory. Why am I doing this? What's my motivation behind the project? And the reason is that a few months ago, I was watching Pokemon. And during my journey, I realized that our dear protagonist, Ash Ketchum from Paletown, is quite incapable at detecting or recognizing Team Rocket under certain circumstances. And this got me thinking, and I was like, could it be that a neural network is actually better than him at detecting Team Rocket? And well, spoiler alert, my friends, the answer is yes. In most cases, yes, it is. And this should not be a surprise, right? Because we have seen all the amazing things that networks are doing nowadays. So for them, this is a trivial case. However, I want to go deeper than that. And I'm not talking about deep learning. I'm talking in the sense that I wanted to know how is the network actually doing this? How is the network reasoning when it sees an image of Team Rocket? How does it know this? What does it see? And of course, I want to know that if we can explain its answers. And most importantly, how can we as the developers or as the maintainers of this model actually get access to this information? Because I want to see once again. So in simple words, my goal here is to explain and to visualize the decision that my model is making. And with that out of the way, let's jump into the agenda. And now, after this introduction, I'm going to present to you the context of my problem, followed by the problem itself, then the experiment, and then the conclusion, which is very sad, but of course, everything comes to an end. So the context, and I want to ask you guys, what is Team Rocket? Exactly. Some of you know, some of you don't. That's perfect. So for those of you who are a bit unclear, I want to say that Team Rocket is the main antagonist of the Pokemon world. And this team is making of the highly explosive Jessie, super charismatic Jane, and super funny Meow. However, for today, I'm only going to focus on James and Jessie. So I'm sorry, Meow. And the goal of Team Rocket for over 10 years has been to capture Pikachu. That's right, this nice yellow rat that we have here, or this one I have here. And for doing so, they employed all sorts of techniques, which includes traps, tricks, and more tricks. And the most iconic one is disguises. That's right. They wear different clothes. They try to hide themselves or pretend to be another person to try to trick Ash into thinking they're someone else. And of course, with the goal of capturing Pikachu. Honestly, they haven't been so successful. And this is an example of them. And here we have Team Rocket wearing a nice and pretty modern black coat and glasses. And I see them as Team Rocket, however, Ash cannot recognize it. And let's actually see an example too, so you can guys have an actual idea of what I'm talking about.
That was really disturbing.
There we have it. So what did we just watch? Well, that was Team Rocket, right? We're dancing, waving some flags with the big letter R. And even with that, Ash is like, who are these people? So that's how I got the idea. Now let's jump in straight to the problem. What exactly I want to solve? For solving my problem, I'm going to split it into three different parts. Which the first one of them, which takes the name of my presentation, is a neural network better than Ash at detecting Team Rocket. And here I'm going to use an object detection model. For the second part, if so, how, I'm going to employ a convolutional neural network and their activation maps. And before moving on, I want to quickly say that an activation map is the output of the layers of my convolutional neural network. And by looking at them, we can get an idea of the most important, primary, or even dominant features of the image. And then I want to interactively visualize the activation maps. In other words, I want to build like a nice web application with buttons and slider where I could upload the image and then see the activation map. And for doing so, I'm going to use TensorFlow.js because my networks are going to be trained in TensorFlow. So for the first part, here, once again, I'm using an object detection model. And the goal here is to detect Jesse and James in a frame, which is an image. Then I also need to mention that I trained this model using Google Cloud AutoML, which is not free, but you get 100 free node hours, which are more than enough for training such a small and prototype model. Then I want to say that my model is an edge model. An edge here refers to a model that is highly optimized and capable of running on small and simple devices like mobile devices, embedded devices, and the web browser. Then for the second part, if so, how? And here I have this network, which I'm calling RocketNet, and I train it in TensorFlow. And the network is just going to solve an image classification problem, meaning that it's going to predict whether this is Jesse or James. And however, as I said before, the actual goal here is to know how it is predicting that. How does it know that it's Jesse and James? And the answer lies in the activation maps. Now, here, once again, I want to interactively visualize my activation maps. And for doing so, I'm going to use TensorFlow.js. And here, there are three things I need to do. The first one of them being converting my TensorFlow convolutional neural network to TensorFlow.js. Then I need to load my Google AutoML Edge model. And then, of course, I need to build the rest of the web application. Sorry, yeah. So, the experiments. So, the data. There's no machine learning without data, right? And my data set is fairly small. It consists of 158 images of Team Rocket, where 87 are of Jesse and 71 are of James. And even so, if it's really small, it should be fine because Google recommends at least using 50 images per label at the time of using the AutoML platform. And even better is that when you use Edge AutoML, Google is actually leveraging transfer learning. So you won't train your model from scratch, which is nice. So you have like an extra bit of help there. Then for the image classifier, I'm going to increase my data set using TensorFlow's image data generator. And here I want to show you a small sample of my data set. In the top row, we have Jesse, and below we have Jane. And the point I want to illustrate here is that my training set consists of only images of Team Rocket wearing their normal white suit or outfit, because I don't want my network to see Team Rocket and their disguises. And I actually wanted the network to have the same thinking process as Ash. And since Ash is a bit bad at detecting Team Rocket when they're using outfit, that's what I want the network to have, to be on the same level as Ash. Now, this is my image data generator. And before you start to take some screenshots, just relax and enjoy, because at the very end of the presentation, I'm going to show you a link to my GitHub repo where I have all the code here. So it's nice, just enjoy for now. Now, the data generator. And here I'm going to do several things to augment my data set. The first one of them is rescale. And this one is going to rescale my image. Then I have rotation range. And here with this, I'm going to randomly rotate my image from minus 45 degrees up to 45 degrees. Then I'm going to shift it in terms of width and height. Then I'm going to horizontal flip it. Then I'm also going to zoom in. And lastly, I'm going to use 20% of these images as the validation set. Now, the first model, the object detection one. And this model, it's trained in Google Cloud AutoML. So everything you're going to see here belongs to the Google Cloud Console, which is full of buttons and nice blue colors. So let's begin with the first step. And the first step is to annotate and create my data set. And here, first, we need to go to the dataset management page. So on the main screen from the Google Cloud Console, search for dataset, Click, and this will take you to a screen that looks like this. And here first, you're going to give a name to your dataset and to select the objective, which in my case is object detection because I want to train an object detector. Makes sense. Now we need to annotate the dataset. And annotate the dataset refers to the amazing and super boring process of drawing bounding boxes around the target of my training, which is Jesse and James. And this is very time consuming. So maybe you should watch some Pokemon in the background while you do it. Don't know. Maybe you'll like it. Then after that, you're going to train, which is the part we all like and love. And here first we need to define the model, which means giving it a name and selecting whether you want a cloud-hosted model or edge. I want edge. You click continue, and then you select the model optimization mode. And this refers to whether you want a very fast model, which is not so accurate, or a very slow model, which is a bit more accurate. I want neither of those. I want the best trade-off. So I'm just going to select the option in the middle. Then, boop, continue to select the node our budget. And here, just select the default value, the recommended one, which once again should be enough because you have some free node hours time. So that's nice. Now, after clicking that, the model is going to start the training process. And it's going to take around 1 or 2 hours. So you can go out, take a walk, get a glass of water and whatnot. But beware of your phone, because once the training is done, you will receive an email from Google. And if you click it, you're going to see a screen like this. And here we have the model evaluation. How did it perform during training and during the testing phase? And in my case, during testing, the model achieved a precision of 100%. Great. And a recall of 93.75. After that, if you're happy, you click another button to export the model. And here you have 3 options. TensorFlow Lite for mobile devices, TensorFlow.js for the web browser, or container in case you want to deploy your model in a Docker container in the cloud. I'm going to select the middle one because I want to use TensorFlow.js. And this is going to give you one file that after open it, it's going to contain 3 kind of files, with the first one of them being model.json. A model.json describes the topology or the architecture of your model. The next one, dictionary.txt, has the labels, which in this case is Jesse and James. And the last one, the bin files, they represent the weight of your model. Now we have the model, it is exported, and I want to use it in TensorFlow.js. How am I going to do this? Well, with AutoML Edge API. And AutoML API is a small package that provides you all the tools that you need to load and to predict with your model. And here on the second statement, I'm going to use the function called tf.automl.load object detection to load my model. And the only thing you need to specify here is the path to the location of your model.json file. Fine, right? Then I'm going to use model.detect to predict. And the first parameter here is my image. And the second one is an optional object, which I'm calling model option. And model options, you're going to select some attributes that you want regarding your detection part. For example, score. And score specify the minimum confidence value a prediction has to have for it to be returned. In my case, it's 0.80, meaning that if the prediction's confidence value is 0.79, it won't be returned. Then I have top K, and top K is going to return only the K prediction that has the highest confidence value. In my case, I only want 5. Now, let me actually show you some of the results here. And ta-da! Jesse. Amazing, right? Jesse 0.93 confident. If you remember the video from before, Ash was not capable of actually detecting this. So neural network 1, Ash 0. But hey, what do we have here? That's James, indeed. That's James. Well, good job, network. Good job, network. 2 points. Ash, 0. And guess what? More correct predictions. Woo! Jesse and James. 0.98, 0.95. And hey, guess what? More predictions. Jesse and James. It's crazy, right? It's amazing. I'm super happy. This model is perfect, and it is not. Of course it's not. The model also fails. And I realized that in cases where the images are a bit too goofy or too funny, the model is actually not capable of recognizing Team Rocket. Also, we have cases like this where it's quite hard to actually see who's here. For example, I'm pretty sure that if I would stand all the way here and take a look at my image, I'll be like, I think that's Jesse, but I'm not so sure about it. So it's okay, network. I'm going to forgive this one because it's not a straightforward case. And then we have the awful cases where I have Jesse and James in the same frame, and the network is actually not capable of giving me both labels. Just giving me one, Jesse, and well, it's kind of right, but this is Jesse and James. Where's James here? So yeah, that's actually quite boring. So is a neural network better than Ash at detecting Team Rocket? Well, it's a bit better, right? What do you guys think? Before moving on, I'm sorry for that. Now, I want to go to the last part of my presentation, the image classifier and the activation maps. And to start, I want to show you the architecture of my network. And the network is very small, very simple. It only has 9 layers, which include 3 convolutional layers, 3 max pooling layers, 1 flattened layers, and 2 dense layers, with the last one giving me the output, which is Jesse or James. And this is a visual representation. Here we have the first convolution, max pooling, convolution, max pooling, convolution, max pooling, dense, and dense. And this is the evaluation. How did my model perform during training? And the accuracy is quite good for both the training and the validation set. We have 0.86 and 0.80, which is great, right? The same can be said about the loss value, which is also very, very small, 0.37, 0.38. So now I have my model. It is trained. It's amazing. I love the results. And once again, I want to use it in TensorFlow.js. So I need to convert it. And for doing so, I'm going to use this small tool called TF-JF converter. And the tool is very simple to use. You only need to specify the format of your input model, which here is Keras save model, and then the location of my model and the location where I want to save the model. And before doing so, there's 2 things we need to keep in mind. And the first one of them is that TensorFlow.js supports only a limited set of operations if you compare it to TensorFlow. Meaning that if you have a very complicated or complex model and you try to convert it, chances are that there might be one operator that is not yet part of the TensorFlow.js API. So in this case, the conversion is going to fail. Then I also want to say that you should install this tool in a virtual environment or in Docker, because it's going to install a version of TensorFlow, and this might cause issues if you already have another version of TensorFlow in your computer. So once again, limited set of operation, and please use a virtual environment. So now, the very last part, visualizing the activation maps. And the main idea here is to recreate my model in a way where the outputs are going to be the activation maps of each of my layers. And for doing so, I need to convert my model to the sequential API to the TensorFlow functional API. Now, if you have trained a model in TensorFlow, the chances are that you have used the sequential API, which is like the normal one, where you have layers, or where you have like a stack of layers. Layer 1, layer 2, layer 3, 4, 5, 6. That's good. However, in the functional API, you need to specify, you need to draw the graph between your layers. So you have, the layers are like kind of laid down on a table, and then you have to make the connection between them without making a cycle. TensorFlow does not like cycles. And here, you need to specify the input as well as the output. And for this new model, I want to use the same input as I have in my previous model. So the input of my first sequential model, of my first image classifier, is going to be the same one in this model. However, the same is not about the output. For example, if you remember from my first sequential model, the output is the dense layer, which give me the label, Jesse or James. However, in this case, I want the output of my functional model to be the outputs, plural with S, the outputs of my convolutional and my pooling layers, meaning that the output is going to be an array of length 6, because I have 3 convolutional layers and 3 max pooling layers, where, I'm sorry about that. So the output is going to be an array of length thicks, where each entry is the output of my convolutional and max pooling layers. And this output, these are the activation maps. So after predicting, I'm going to have one array of length 6, where each entry is the activation maps of each of the layers. Now, let me show this quickly in code, like what exactly I'm talking about. First, I'm loading my first model, the normal object classifier I trained in TensorFlow using the sequential API. Right. Now I'm going to create one empty list called output layers. Then I'm going to iterate over the first 6 layers of my network, boop, 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 while pushing to this list the output of the layer. Again, iterate over the first 6 layers, which are the convolution and max pooling, and then I'm going to append to my list the output of the layer. Then I'm going to create my model using tf.model and using as input the input of my first model and the output of the sorry, and as output the output of my convolutional and max pooling layers. In TensorFlow, it's the same process. First, I'm loading the model. Then I'm going to create one list called output layers. And then I'm going to create my activation model. Cool. So yeah, the prediction output is the activation maps of the 6 layers. However, we need to go a bit deeper than that because these layers, they have filters. So when I'm talking about the activation maps of my layers, I'm actually talking about the activation maps of the filters of my layers. And for doing so, I need to create I need to index more stuff here. For example, I need to specify which layer I want to draw and which filter of this layer. So for doing so, in my web application, I built some kind of helper function where first I'm sending the complete set of activations. Then I'm going to use the layer of the index I want to draw. And then I'm going to use the filter I want to draw. And you don't have to pay attention to this. I just want you to see the third line where you can see all the indexing I'm doing. So I'm indexing the layer, and then I'm going to select the filter I want to draw. For doing so in TensorFlow, it's the same thing. On the first line, I'm getting the first layer. And on the second line, I'm going to specify which filter I want to draw using filter number. And then I'm going to show it on screen. So now for the final app, this is how it looks like. And here we have the first part of my application where I can see where it is showing me the object detection. Very similar to the thing we saw before. We have one image, we upload the image, we get the prediction output, the label, and the bounding box. And now this is the cool part, the activation maps. And here I have the activation map section of my first layer. So since I have 6 layers, I actually have 6 groups of this thing that you see here, 1 per layer. And under the label, under the name of my area, which here is convolutional 2D layer activation, I have a small slider that I'm using to select the filter I want to draw as a heat map. And then below that, there's the heat map itself, where I can see the output of my filter and the activation. And here we have like the values. And the highest the value is, it means the most important that part of the image or that feature is to the classification. And the lowest the value, the least important this part of the image is at the time of making the prediction. And now let's see a proper example. And here we have Jesse. And now it's time to answer the main question here. How is the network capable of doing this? What is the network looking at? And the answer is the hair. Is anybody surprised? Is anyone surprised? I guess not, because of course, that's the most common, the most dominant feature of Jesse, the hair. And that's exactly what I wanted to solve. So problem solved. Super happy. And here we have 6 different activation maps, 1 per layer, and just using one random filter that I don't really remember which one was it. And we can see that in all of them, the main feature of the image, of this activation map is just Jesse's hair. And also you're going to realize that as we go down, the first image corresponds to the first layer, second layer, third layer, blah, blah, blah. And then you can see as we go down, the resolution gets lower and lower because that's how it works. Now for another example. this one with James. And the result is almost the same. We have a lot of focus on James' hair, even including his beard on image number 5. But once again, sometimes it fails. For example, here, this is the same image as before. And if you take a look at the activations, well, they're all over the place. We have high values, like even in the background of the image, which is totally wrong. So, and that was it. Now for the takeaways. And I want to end this by saying that, in my opinion, right, explainable AI is as important as AI itself. And as we keep building and deploying artificial intelligence solutions everywhere, we need to keep in mind that these tools, as great and amazing as they are not, it's not fully, how do I say, they are not fully easy to understand. And we're making a lot of decisions that are improving our lives. So we should actually be more careful. We should take care about exactly to know why the model is doing this. So we should explain, just in case something happened and we need to give an explanation to someone, which could be your boss, for example. Also, I want to say that, in my opinion, once again, a web application is a suitable platform for a data product, and we don't see them quite often. Normally, we have Python script, Python notebook, and so on. But I like working on the web because you have the complete ecosystem that JavaScript has to offer. So you have like buttons, library, graph, and whatnot. Also, I want to say that the compatibility between TensorFlow.js and TensorFlow is improving vastly. So which is passing day, it is even easier to convert one model to the other. Also, if you know one of the platforms, it's quite easy to use the other one since their APIs are very similar. The only thing you need to keep in mind is just the particularities of the language itself. Last, I want to say that empirically speaking, the networks are better than Ash. And why is that? Well, because they look at Tim Rocket's hair. And now I also want to repeat and say that this was a very, very fun project. So thanks a lot for your time. It's been a pleasure to be here. Here you can see several links, which the first one pointing to the GitHub repo. And here you have all the code, including all the training set and testing set. Then I have an article in case you want to read the whole process. And there's also one demo. And in the demo, you need images, but you can find them in the GitHub repo. So I hope you guys had an amazing time. Hopefully, I hope to see all your questions, regards, comments, and whatnot. And feel free to contact me either here in the chat or on Twitter. So thank you and happy PyData. Bye.